Okay, so away you go, Antonella.
Okay. Good afternoon. I'm Antonella Toffetti, and I am very happy to give you my and the executive board members warm welcome to this Human Factors and Ergonomics Society Europe chapter autumn event, a Stephen Fairclough remote keynote. As you may know, due to pandemic period restrictions, we had to postpone our usual autumn 2020 and 21 conference to April 22. Then we thought to some online events. Beyond the discussion with Don Norman organized last spring, the Human Factor Ergonomics Society European Chapter Board decided to involve keynote speakers of our previous annual conferences to deepen with them how their research evolved in some years after their first talk at our meetings. We invited Professor Stephen Fairclough, keynote in Rome, and he kindly accepted to be our first remote keynote speaker. Thank you very much, Steve. We appreciate. Just a short introduction to Professor Stephen Fairclough. Stephen Fairclough obtained his PhD in psychology from Loughborough University in 2000. He is currently a professor in the School of Psychology at Liverpool John Moores University. His research is concerned with applied neuroscience in the context of human factors. He also has an active research interest in human-computer interaction, particularly using data from neurophysiology and psychophysiology as a control input to technology. He is currently one of the editors of the journal Frontiers in Neuroergonomics on the specialty topic of neurotechnology. His talk is entitled "The Role of the Prefrontal Cortex and Functional Connectivity during Watchkeeping and Collision Avoidance during Maritime Operations, a functional near-infrared spectroscopy study." Before starting, thanks to our past president, Steven Rotger, for organizing the remote keynote, and to one of our co-director, Denis Coelho, for organizing the Zoom connection. If you wanted to ask something, please use the chat, and Steve will answer after his talk. Now we can start. Thank you again, Steve, for being here. It is a big pleasure for us to listen to your talk. The floor is yours.
Thank you very much, Antonella. I'll just set up my screen share. I should say while I'm doing that there is, I think, the facility on this for you to raise your hand at the end of the talk if you want to ask questions, and I will be able to allow you to ask them on the system. So hopefully you can all see my my first slide now. So as Antonella's already said, I'm going to be talking today about some work on human factors in maritime operations using neurophysiological measures. And this particular piece of work was a collaboration between myself and the School of Maritime Engineering at Liverpool John Moores University, and particularly between myself and Shiki Fan. And Shiki was a PhD student, and it is part of her PhD work that I'm going to be presenting today. So let me begin by setting up some context for you. I'm sure that a lot of you will be familiar with things like physical ergonomics and cognitive ergonomics. So today I'm going to be talking about an example of research from the field of neuroergonomics. Now, neuroergonomics was originally defined by Raja Parasauraman as a scientific study of brain mechanisms to technology, work, and environments. And that reflects his background in human factors and cognitive neuroscience. And the field of neuroergonomics is generally focused on studying neuropsychology in the context of safety critical systems. Now, since that original work, the field has grown. The community had its third international conference last month. And now the field of neuroergonomics is expanding to look at beyond safety critical systems and to look at the study of the brain in everyday life. So as you can see from these pictures, we see people using measures of brain activity in all kinds of real world sort of situations. Now, the primary factor that I think is driving the growth of research in neuroergonomics is really the evolution of sensor technology, particularly in the area of mobile EEG. And what I'm going to be talking about today, which is fNIRS, which means functional near-infrared spectroscopy. That's an optical method of neuroimaging. And what it means is that we're able to use these methods across a range of different scenarios, from highly controlled settings to real world settings. And it means that we can expand the field of research to extend into more real life situations. Now, generally, we would say, I think this is a good thing. And I would say, yeah, it's definitely a good thing to be able to take brain measures into the real world, but with a couple of caveats. First of all, the largest one is that when you add neurophysiological measures to the study of real world behavior, because these measures are kind of quite challenging technically to get good data in the real world, you do have to ask yourself, what added value does it actually bring to the science of the human factors investigation? As much as I do enjoy seeing pictures of pilots on planes wearing EEG caps, or even a picture of a guy on a climbing wall with EEG apparatus on, while it looks nice, but what actual insight does it offer above and beyond behavioral measures or other measures like eye tracking? So I'm going to return to that question at the end of my talk, but just bearing in mind is that if we're using brain measures in the real world, they have to offer genuine utility and value to our research. Now, let me set up the background for this particular study. Now, my original background in human factors was in driving behavior, and I understand very well why cars collide in the real world on real roads. But it seems to me surprising that ships still collide, and in fact, collisions between vessels is the most second common form of accident at sea. Consequences of these sort of accidents are perhaps less concerned with loss of life in most cases, but more with the environmental damage and the financial cost that is concerned. So why do ships collide? Well, sometimes due to errors of navigation or mistakes made in maneuvering, simply turning in the wrong direction. But when we look at the underlying causes behind these accidents, we find that these things tend to be attributed to what we call perception failures. So the misinterpretation of available information and loss of attention. Now, watchkeeping describes a scenario where officers must observe and record the position of the vessel at regular intervals while paying attention via visual lookout and onboard apparatus to what is going on in the immediate vicinity of the craft. 2/3 of collisions that occur at sea originate from insufficient watchkeeping. And part of that insufficiency stems from problems related to sustaining attention. So part of the problem is a vigilance problem in a way, and the other part of the problem is making that transition from doing nothing for a long period of time to suddenly having to respond to an unforeseen event. And analysis of collision accidents often point towards not just failures of attention, but failures of planning, incorrect assessment of the situation, failure to plan forward into the future. So the problems of vigilance and sustaining attention, I think, are well known in human factors psychology. But we're going to look at this issue from a neuropsychological perspective in this particular study. Now, in terms of the neuroscience of vigilance, early work in the 1990s identified the right lateral area of the dorsal prefrontal cortex as being particularly important, whereas we know that people who have damage to this area of the brain really do struggle to pay attention over periods of time. Now, subsequent meta-analyses reinforce the importance of that area, but also the link between that area and an area of the cortex that we call the right medial part of the dorsolateral prefrontal cortex. So there's a right lateral part and basically the right part of the middle area of the prefrontal cortex. The communication between these two areas of the brain seems to be particularly important in vigilance, and it does, and especially when tasks don't require regular motor input. And that connectivity is something that we see across both visual and auditory modalities. So that's a little bit about the neuropsychology of vigilance. The second component of our task and of the talk involves planning and action preparation. Now, there is a model from cognitive neuroscience from Kolchak that proposes that when we plan for action, the prefrontal cortex is involved in a hierarchical fashion, depending on the novelty of that action that's being planned. When selection is informed by recognition of context and previous encoding or in memory, the model presents evidence of bilateral activation, as you can see in this picture on the right, of the left and right sides of the prefrontal cortex. And so the basic idea behind our study is that we would use an optical neuroimaging method, like fNIRS, to measure activation and connectivity across the prefrontal cortex during a watchkeeping task that incorporates elements of both sustained attention and action preparation. Now, the study was conducted on a ship bridge simulator that we have in the Maritime Engineering department of our university. So here's a picture of that facility. So as you can see, it's got a 360-degree screen. There is enough room in there, so it replicates the console of a ship's bridge, and there's enough room in there for maybe 2 to 3 people to work together. This facility is generally used to train people. People from industry come to the university to get training qualifications as maritime operatives. So in our particular study, we simplified things significantly. The participants sat in a chair, and we restricted their view to only the forward 180 degrees of the view. We made this restriction generally due to the effects of to limit the effects of large-scale head movement, which does have an effect on the fNIRS signal, and obviously large-scale physical movement as well. So, and this was really the view that our participants saw when they were doing the tasks. They sit, they look forward, they've got the wheel of the ship in front of them, they've got some other instruments, and they basically just see a mostly empty seascape in front of them. And what we told our participants to do is that they must monitor the forward view, do normal watchkeeping, and if they spot another vessel, they must first of all verbally report that they spotted another vessel, and then they must monitor that other vessel. And if it was necessary, then they should alter the course of their ship to avoid a collision. So that was the basic instructions that we gave to the participants. The way that we set up the experiment is that we had the participant vessel, which you can see in the bottom here, and we had a target vessel that would approach very slowly from one of 10 different locations in the forward view. And the participant vessel continues on its own shipping lane. So what happens is that the target vessel is actually on a collision course with the participant's vessel, and at some point they're going to have to make an evasive maneuver to move out of the way. We found generally that our participants would spot the ship 22 minutes after the experiment began, and then they would spot the ship, and then they would have to monitor the ship and monitor its course, and then decide whether they needed to make a maneuver or not. But all these things unfold kind of quite slowly over time. So when we look at our independent variables that we have for the study, what we basically have is a number of different periods. We have a period of sustained attention, which is watchkeeping, which is generally just looking at the empty sea. And then we have a period of action preparation and decision making where a ship has been spotted, and the participants must then decide whether they're going to move out of the way of the ship or not. Now, in general, as I said before, most people spotted the ship after approximately 22 minutes of watchkeeping. And what we did was we divided those 22 minutes equally into 4 periods. So we have 4 periods of watchkeeping. And then when we have this dotted line here, this is the point at which they say, I can see another ship. And then at this point here, these 2 decision-making periods, they are monitoring the other ship and deciding whether they have to move or not. And in general, they took 10 minutes after they spotted the ship. Most people decided to, I think everyone made the evasive maneuver. So that's the experimental task that I'm going to be talking about today. Now, in terms of the other aspects of the experimental design, we used a between participants design because we recruited 40 people, but we split them into 4 different groups. Now, because we run courses to train maritime officers at my university, we were able to recruit participants who were already familiar with the bridge console and watchkeeping, but they differed according to the level of experience. That means actual experience of being at sea. So the other thing we did is that we introduced an additional distraction task to increase the mental workload for half of our participants. And I'll say more about that in a moment. So we've got 4 groups of 10 participants within our 40. Half do the distraction task. 20 of them are classed as experienced maritime officers. And on average, these experienced people had spent 213 months at sea. And the other group are inexperienced. They'd spent 27 months at sea on average. Now, obviously, our experienced group tended to be older than our inexperienced group. So the average age of the experienced group was 44 versus 25 for the inexperienced group. And the majority of our participants were male. There were 3 females in the whole sample, 2 in the inexperienced group and 1 in the experienced group. And this distraction task that we introduced to increase mental workload involved monitoring one of the ECDIS display. So there's the ECDIS display that you can see here, and it's basically, that stands for Electronic Chart Display and Information System. And this display shows the position of the vessel on a nautical chart, and our participants are required to verbally report their position over an intercom to a senior officer, who was a person running the simulation, and they had to report that when the craft passed every minute of latitude on the chart. So this really corresponded with them reading out a detailed description of their course once every 3 minutes. And so they have this additional task of monitoring the display and being able to do that as well as the other tasks that I've already described. Now, so there's our independent variables in the way we set up our experiment. Now let me say something about the things that we actually measured. The piece of significant apparatus for us is the fNIRS apparatus that was used to measure the neurovascular activation of the cortex. Now, fNIRS, for those of you who don't know, is an optical method of imaging levels of oxygenated and deoxygenated hemoglobin in the upper 2 to 3 centimeters of the cortex. And the way it works is that you have an emitter and a detector, and the emitter sends infrared light that goes through the skull into the brain, and then the amount of infrared light that is reflected back is collected by the detector, and on the basis of that, we're able to assess the level of oxygenated and deoxygenated hemoglobin in the cortex. And what you generally expect is that when the cortex is activated, you have an increase of oxygenated hemoglobin and a decrease of deoxygenated hemoglobin, which is something we call neurovascular coupling. So we're going to focus particularly in this talk on increases in oxygenated hemoglobin. And for this particular study, we used an fNIRS system made by a company called NIRX, which is called the NIRX Sport. And it's a kind of an ambulatory system. You kind of wear it in the backpack, as you can see in the picture here. So you can, in principle, use it, wear it, and move around, although we restricted that for this particular study. Now, in terms of the montage, by which I mean which part of the brain did we actually monitor, we were focusing on the prefrontal cortex. Now, our particular system had 8 sources and 8 detectors, and they were configured, as you can see on these 2 diagrams, in order to yield 15 channels of fNIRS data. So the numbers are the actual channels of fNIRS data that we receive. We used the 1020 system from EEG in order to position the optodes on the cap in exactly the same way you would do for EEG. And we tried to cover the full range from the right to the left and the medial areas of the prefrontal cortex. So here's an image of Shiki setting up the system with a participant. And you can see they're sat in a chair, and so we didn't have too much movement. And on the right side, you can see that we have these 15 channels, and these 15 channels are split into 3 regions of interest. 1 is the left side, the left lateral side. 2 is the central or medial part, and 3 is the right side. And I've also included for completion the 1020 coordinates for those things. And for those who are literate with the cortex, these are the Brodmann's areas that are associated with each of those things as well. Now, in terms of collecting and analyzing fNIRS data, like a lot of these things, there is a signal processing pipeline associated with it. The fNIRS signal is recorded at 9 Hertz. The raw data that we get from the fNIRS signal is something called optical densities, which is how much infrared light is returning to the detector. And the fNIRS the NIRS software that we use for this particular one has a signal processing pipeline that does a number of different things. First of all, the signal is checked for any spikes or discontinuities. So if someone moved their head quickly and the optode slipped on the scalp, you'd see a big spike in the data. So they're detected and collected and corrected with interpolation. The fNIRS signal also picks up physiological activity from the body, such as heart rate, respiration, and cyclic fluctuations in blood pressure that are called Mayer waves. We use a low-pass filter to try and mitigate the effects of those things. And then this optical density data is translated into oxygenated hemoglobin using something called the modified Beer-Lambert law here. And we also used another procedure called CBSI, which is a correction-based method to correct for any artifacts in the data. So there's a fairly involved signal processing pipeline when we collect fNIRS data for this sort of work. Now, for this presentation, I'm going to talk through 3 different sets of analysis, in effect. I'm going to talk about behavior. I'm going to talk about neurovascular activation, by which I mean the mean level of oxygenated hemoglobin. When I use the acronym HBO, that means oxygenated hemoglobin from left, medial, and right regions of interest. And I'm also going to be talking about connectivity analysis at the end. So first of all, let me start with the thing that's easiest, I think, for everyone to understand, which is behavioral measures. So we were interested in how far were they from the target vessel when they spotted it originally, and how far were they from the target vessel when they made an evasive maneuver, operating on the understanding that when they spot the vessel farther away, and when they make an evasive maneuver when they're farther away from the target vessel, then this is better for safety. So we calculated those mean distances and we subjected them to an Manoeuvre analysis, and we found no difference at all for either the effects of distraction or experience on the distances at which the ships were spotted. But we did find differences in terms of the experience of the participant in terms of when they performed an evasive maneuver. So here's a visualization of that data. It may be one that you haven't seen before. This is called a rain cloud plot. And what you can see here is the green data is our inexperienced participants, and the red data is the experienced participants. And in the upper part here, this is a probability density. So this is a distribution of the data. And then here, this is basically like a normal box plot. So here are the means, so the vertical lines and the confidence intervals, and the dots are actually the raw data. So what we found was that that our experienced people basically made an evasive maneuver when they were further away from the target vessel compared to our inexperienced people. But the reason I like this visualization, because you can actually see everything, all the data on it, is that you could see that that is mainly caused by this skew in the data. So you see that our inexperienced people, a group of them happen to leave it a little bit later than the rest of them, and this is why we're seeing this effect. It is significant, but only at like 0.04, I think, and the effect size is 0.11, so it's not a big effect size. And you can see that's because it's really down to this skew from a minority of our participants. And these rain cloud plots and some of the other visualizations I'll use, I'll put some links into those at the end of the talk if you're interested to find out more about them. Now, the next piece of data I'm going to show you is the oxygenated hemoglobin, and this is oxygenated hemoglobin from the right lateral region of interest, so the far right side of the prefrontal cortex. And what you're looking at here is the level of oxygenated hemoglobin over our 4 periods of watch and then our 2 periods of decision through the whole workflow. Now, this is another data visualization you might not have seen before. This is something called not a box plot. It's actually from MATLAB. It's a MATLAB resource. But what you're seeing is the red horizontal lines are the means. The pink areas are the standard deviations. The blue are the confidence intervals, and the gray dots are the raw data. Now, it may not look like it from this particular plot, but the level of oxygenated hemoglobin was significantly lower during the 3rd and 4th periods of our watch activity compared to all of the conditions. So as we might have expected, when people do a vigilance task, do a sustained attention task, looking at an empty seascape for a long period of time, you get lower and lower levels of oxygenated hemoglobin, especially in these final two sequences here, which then kind of increases slightly when we get into the decision-making part of the task. So we can see this kind of pattern here starts to emerge where oxygenated hemoglobin declines over watchkeeping, then gently starts to increase as people enter a phase of more active cognition. Now, we also found an effect for phase here, and here's another version of the rain cloud plot, but this time for repeated measures. So what you're looking at here is the second, third, and fourth period of watch activity. So that's literally, I think it's, let's see, that'll be 10 minutes, 15 minutes, and about 20 minutes of watch there that you're looking at. Again, the inexperienced people are green, the experienced people are red. And you can see here that we have a higher level of oxygenated hemoglobin for our experienced participants during that final key period of watchkeeping. Now, you've got to remember that during the final key period of watchkeeping, this was a period just before they confirmed that they had spotted a vessel in the distance. So my feeling is that our experienced people were probably thinking about, they probably could see a little dot on the horizon and they were trying to figure out if that was a ship or not, and they were possibly a little bit more alert to that than our inexperienced people. But again, as you can see here in this fourth watch period, the inexperienced people are characterized by this long tail here. So maybe a minority of people, a minority of our participants in the experienced group are really not paying attention at that particular point, or not paying sufficient attention, I should say. So let me recap where we are so far. So we have, as we would have probably expected, activation in the right lateral area of the prefrontal cortex, which has in laboratory studies been associated with vigilance. It declines during sustained attention. It tends to increase during active decision-making, and we find it's higher for our inexperienced people in the final period of the watch. Now, the next analysis I'm going to talk about is a connectivity analysis. So let me just say a couple of things about that. So normally when you do analysis of brain activation in any kind of setting, you can look at differences in activations in different parts of the cortex. So basically this area is more activated than this area. But as we know, the brain is a massively interconnected system. So another way that you can look at these kinds of data is by looking at the level of connectivity between them. It's basically to treat the area of the brain you're interested in as a network and understand the connectivity within that particular network. Now, in our particular case, this is the montage that we had. So we basically had these 15 nodes. So imagine there are just 15 nodes on a network. And at any one time, one of those nodes could be co-activated with one or more of the other nodes on the network. So even in a small, relatively sparse network like this, we still have 225 possible paths that could be active at any one time. Now, in order to measure that, put metrics on that, and be able to analyze that pattern, we turn to a branch of mathematics, which is called graph theory, which is a way of mathematically characterizing different networks. So when you formally define a graph or a network using this approach, you're really trying to describe the relationship between nodes, which are also called vertices, and edges, which are links. So the links, the edges, give us our patterns of co-activation. Now, for our analysis, I used two very, very simple measures of network activity in order to describe frontal connectivity in this particular study. The first one I used is called density. Now, in density basically expresses the wiring cost of the network. So out of all the available links that are possible within the network, how many are active in any one time? In a network like this really simplified one I'm giving you as a hypothetical here, we have 4 nodes and we have 5 possible connections. So that's a maximal connection density we can get. And then if we got, roughly only 3 paths are active, then this is the density that we get, and so on. So connection density is always between 0 and 1. The second measure we use is a little bit more complicated, but it basically expresses the level of local clustering, the level of connection around the node that you're interested in. So in this particular case, we're interested in the red node, and this red node has 3 neighbors. So local clustering expresses the level of connections that are active between those neighbors. So when all 3 are active, it's maxed out. And if one of them are active, then you see the score falls. So we've got 2 different sorts of measures of connectivity. One is talking about density across the whole network in global terms, and the other one is talking about local clustering around the different nodes. Now, how do we get to a point where we've got data from fNIRS, in this case oxygenated hemoglobin, to these sorts of graph theory analysis? Well, there's a number of stages that you have to go to. First of all, when we're doing connectivity analysis, we're interested in association between the different nodes. So the first thing we do is that we calculate a correlation matrix for all 15 channels for each participant for each different period of time that we're interested in. In our particular case, we use partial correlations because they are much more conservative. A partial correlation basically controls for the number of possible correlations that could be available at any one time. So we basically use our partial correlations and generate a correlation matrix, and we throw away any correlations that are less than 0 because we're only interested in positive associations. Then we apply a threshold value to discriminate significant correlations from insignificant ones. Now, there are a variety of different ways to do this, and in some ways, this is perhaps the most controversial part of doing these kind of connectivity analyses. In our particular case, we found out what the significant correlation would be for a normal Pearson's correlation, which is 0.25, and we used that as our criterion. And we used that because we thought it was still fairly, because partial correlations are basically much more conservative, we thought it was still it was good to take the threshold from a normal Pearson's correlation to do that. So what you then do when you have your threshold, you basically say, okay, anything above that threshold is a 1, anything below that threshold is a 0, and then you create what we call binary adjacent matrices. So this is this thing that looks like a crossword pattern here. So anything, all the whites are 1s, all the blacks are 0s, and so basically, after you get to that point, you can then calculate density and clustering based on these grids, these adjacency grids. And we used a MATLAB tool called Brain Connectivity Toolbox that was put together in 2010, and we used that to calculate the level of density and clustering for each participant, and then we subjected those to an ANOVA. So let me talk about the density data first of all. So here's our plot of density data. So what you see kind of quite clearly is that density is fairly consistent over watchkeeping, but then it drops when people enter a decision-making period of active cognition. So what is going on there, I think, is that the network over the frontal cortex is basically being pruned to its essential components as we switch from a passive monitoring situation to an active decision-making situation. So we have fewer active connections because the network is becoming more efficient and is only preserving those connections which are the important ones. So we see a drop in connection density when we get to the decision-making part of the task. Now, we also found that when participants experience the distraction task, and you can see that the greens are people with no distraction, the reds are people with a distraction, is that we got a significant difference in density during the final period of watchkeeping. So we think what is going on here is that the added workload associated with the distraction task, plus the added workload of trying to figure out if that's a ship on the horizon during the final phase of watchkeeping, basically starts to move people into a stage of active cognition that's associated with a lower level of density. But I've got to say, that's a speculative interpretation. Now, if we look at clustering, we see a different sort of pattern, but it is kind of complementary. The big pattern basically is the level of local clustering massively increases when people are in these active decision-making parts of the task. During the watchkeeping part of the task, you can see that it's not really clear on this, but basically we have a significant decline. So local clustering is lower during watchkeeping 4 than it is during watchkeeping 1. So what is going on here? So what this tells us really is that the level of local clustering pocketed around the different nodes is falling all the way through watchkeeping. And then when we go into active cognition, it sparks up again. And we generally have a higher level of local connectivity during that. So now these density and clustering sort of measures are really interesting, and they show nice global patterns of changes in connectivity. But the one thing I'm kind of interested in, as someone who's interested in the brain and interested in applying it in these sorts of situations, is that this clustering stuff doesn't tell us where those changes actually occur. For example, if density falls during decision making, then what I want to know is which connections are most likely to be preserved at that point. Similarly, if local clustering increases when people are making decision making, where are those local clusters? So in order to answer that question, I'm kind of slightly testing your patience now with these data visualizations. I created a digital data visualization based on something called a chord diagram. Now, usually chord diagrams show the strength of connection between different thickness of lines. Now, I've adapted that here. So let me kind of describe what you're looking at. So the first thing you're looking at is a circular schematic that is describing the positions of the different channels that we had and their associated Brodmann's areas. And what I've done simply is I've counted the number of active connections across all our participants and color-coded them here. So just to save your eyes, if you just pay attention to the red lines and the orange lines, the red lines tell us that that connection was active for over 22 of our 40 participants. The orange lines tell us that between that over 17 and under 21 people, those were active for those people. So now this is the first period of watchkeeping. So you can see we've got a lot of activity done the left side here, a little bit less on the right side, and some bilateral activation across the prefrontal cortex. If we compare that with 15 minutes later during the third period of watchkeeping, so they've basically been staring at an empty sea for 15 minutes at this point, what we then start to see is that all these left side activations tend to fall away. But we see that the right side patterns, particularly at the right medial prefrontal, the right medial prefrontal cortex, which is associated with vigilance, these are still activated here. And these links between the right medial and the right lateral prefrontal cortex, which, if you might remember back from the second or third slide that I showed, these are associated with sustained attention. So these are all still sort of active here. So this is a way of really getting some descriptive data and trying to understand which parts of the brain are active and which parts of the brain are not when we're seeing those changes in connectivity. Here's the third period of watchkeeping. So this is the slide that you've just seen. Now, this is what happens when we go from a period where nothing is happening to the fourth period of watchkeeping, where they're actually seeing a ship they actually think they see a ship on the horizon. So the big difference that you see between these two is the massive amount of bilateral activation that happens between both sides of the prefrontal cortex. I suspect this is due to participants seeing something on the horizon and not quite being sure whether it's another ship or not. So this pattern that we're seeing here is also associated with a decline of local clustering. And I suspect that the local clusters between these adjacent sort of channels here is falling away, because we're getting so much more of these longer bilateral activations taking place here. And then if we go from the final period of watchkeeping, when people think they've spotted a ship, to what happens when they know they've spotted a ship and they're active making a decision about whether to get out of the way or not, then this is what it looks like when we move from that period to that. So first of all, you see the number of active connections falls off dramatically. Remember, density fell dramatically during decision-making compared to watchkeeping. And we also see local clustering increases. So we've got local clusters here all around the medial prefrontal cortex, and we've got some local clustering here in the lateral sort of areas as well. So this is nice from a theoretical point of view, because it's not too far away from the neurocognitive models that have been developed in the laboratory. So it kind of gives you confidence in the stuff that we're finding in the maritime simulator. And it also allows us to take this connectivity analysis and look at it in more kind of descriptive sort of ways. Now, so to summarize really, so density declines in the switch from sustained attention to active cognition. So we've got fewer active connections, we've got pruning basically, got bilateral activation at the medial and the lateral areas of the prefrontal cortex. We also see local clustering increases during this switch from sustained attention to active cognition. So we've got higher local connectivity at medial and lateral areas as well. Now, let me return to the question I asked at the beginning. The whole point of neuroergonomics and neuroergonomic study is to provide insight into safety critical behavior. It's to apply the brain to real world activities. Now, we've certainly found some results in line with cognitive neuroscience literature, which is nice. And I hope you'll agree we've certainly produced some pretty pictures. But what does this applying neuroimaging offer to human factors practitioners or people working in the maritime industry? Why should they care about frontal connectivity or graph theory? Well, here's why. We took density and clustering measures and we created a regression analysis to explore whether those markers could predict safety-related behavior. Specifically, do markers of brain connectivity predict how far away people were from the ship when they spotted it and what their distance was from the ship when they decided to make an evasive maneuver? So here's the result of the regression from when the target ship was spotted. You can see that density, first of all, you can see that 30% of the variance in the distance when the target vessel was spotted was predicted purely on the basis of these two measures of brain activation. And that was surprisingly high to me. Mainly it's density. So we find that basically in this particular case, people with higher levels of density tend to basically spot the ship. People with higher levels of density, it means that the ship is farther away. And also people with higher level local clustering didn't quite make significance, but it wasn't too far away. And it's also in a positive direction. Now, when we tried to use the measure to predict how far away they were when they moved away from the ship, we also see almost a third of the variance is being explained, but now we have a negative association. So people with a lower level of density move the ship out of the way at a higher distance compared to those who didn't. So this is important, I think, because if we're going to go into simulators or even into real ships and use ambulatory monitoring of actual operators, it's important that it offers some insight into safety-related behavior, either as to provide insight into training or to develop neurotechnologies to enhance safety-critical performance or whatever. But it's got to be, the measures of the brain have got to be relevant to the real world. So I will end there. So these are the main findings. Activation of the right lateral prefrontal cortex associated with decision-making. Deactivation is associated with, right lateral associated with sustained attention. And we find these patterns of connectivity in graph theory that I've already mentioned. So I will end on that point. Thank you very much for listening. If you would like to read the full paper, it has been published in the journal Brain and Behaviour, and here's a citation for that. If you would like to know more about some of the data visualizations that I used, there they are for you to see. Thank you.
Thank you very much, Steve, for the very interesting insights, which enrich our knowledge and give us inspiration for our next research. Are there any questions? Do you want to ask Steve?
I'm sorry. I have one in the I have one in from Jared Smith in the chat. So he says, I have a question for HBO measurement. How long was the duration you averaged the HBO over? How long were the baselines before each experimental measure? That's a good question. So someone obviously knows about fNIRS. So these were quite long. They were basically, we averaged this over 5 minutes so each of the periods that you saw. The watchkeeping was between 4 and 5 minutes. Yeah, and the decision making was slightly less, was like between 2 and 3 minutes. And we used a baseline period of 30 seconds before the study started to use our baseline. And just for explanation for everyone, HBO, when you measure oxygenated hemoglobin using fNIRS, it is a relative measure. So you always need a baseline to take it from. So that's why the baselining is important. No, I also think if anybody wants to, you can stick your hand up and I would be able to see that, and you can actually talk on the call and ask me the question. So someone else, Eva, has just asked me, did I try to use any other neuroergonomic methods? Not so far, no. We haven't tried to use EEG, that's what you mean. We've not tried to use eye tracking. This was very much the first study that we've ever tried to do that for. And we're still kind of developing where we're going to go next. So no, we've not tried anything else.
Any other questions?
Yes, Stefan. I got Stefan. Let me just, I think I can click on you. Oh, can you speak, Stefan? Can we hear you?
Can you hear
great.
me?
Yeah.
Yeah, great. Okay, so thank you for your very interesting talk. As I wrote you by email, I'm busy with investigations on seafaring and seafaring teams as well. And right now, I'm planning a study on improving fatigue management and on fatigue at sea. And this is one of the causes of accidents as well, that seafarers are sleep deprived. And that's why don't pay sufficient attention and don't make the transitions from hours of staring at the empty sea to making evasive maneuvers in time. So my question would be, you showed a certain effect of sustained attention on the fNIRS density. So the longer you have to pay attention, or this is associated with a decrease in the density, actually. And are you aware of any study that shows the effects of sleep deprivation on the cortical activity in vigilance or in decision making?
I am not off the top of my head, because really these sorts of connectivity things are generally been the preserve of fMRI studies, like fairly detailed fMRI studies. They have been used in more applied work, but not very often. So we're still at a very early stage of understanding that. I know there is work, I'm pretty sure there is work on sleep deprivation showing that it does affect frontal connectivity, and that we certainly know that people are less able to perform the types of novel problem solving and decision making tasks that are highly creative when they've been sleep deprived, and that activity is certainly associated with the prefrontal cortex. So a short answer is I'm not aware of any work on sleep deprivation per se. I would be very surprised if, you know, the kind of effects that we found on a vigilance task basically were not replicated to an extent with sleep deprivation. But the other thing that would be really interesting to look at would be circadian rhythms, you know, as opposed to sleep deprivation per se. So like, you know, between 2 and 4 o'clock in the morning. Obviously, we did this as a study. We couldn't bring people in for 12-hour shifts, which is normally what they're doing at sea. But that would be the next place to go, I think. It introduces logistic difficulties using this sort of approach if you're doing such long studies, but I don't believe it's impossible to do with some planning. So yeah, I'd encourage you to explore the approach, because I do think it's a valuable approach. I think the nice thing about it is, the really nice thing about it is that you can measure what's going on implicitly without, for example, having to ask people to do questionnaires or do cognitive batteries and stuff like that over and over again, which wake them up effectively. You know, so, you know, as you know, measuring this sort of stuff is difficult, because if you're too active about it, then you ruin the thing that you're actually sort of interested in. So sorry, I don't have any just recommendations for you, but I do think it'd be a really interesting approach.
Yeah. Thank you, Steve.
Okay. I think I just saw a question from Lewis. So hi, Lewis. Would I be willing to make a calculated or wild or intelligent guess? I'll try and do all three on how these measures might contrast from your reported results if you had enough positives or missed events. I'm not 100% sure what you mean by that, Lewis. You mean, oh, I see. I think what Lewis means, and he can jump up on the chat or come into the talk and tell me, is in terms of that we only had one target. So we basically, you either saw the target or you didn't see the target. So yeah, that's right. Yes, I only had hits. Yeah, and we only had one hit, to be fair. Yeah, I'm not sure, to be honest, about that. And I'm not sure how we would set that up in the context of this particular sort of task. I think there is an interesting study to be done. I know from talking to maritime colleagues that when people approach a busy harbour, there is a lot of ships around. So, to put it in terms, in those sorts of terms, you could have some ships that you may collide with and some ships, so they're hits, and some ships that are misses effectively or false alarms that you would not get close enough to. So again, I'm not sure, Lewis, to be honest with you, how it might contrast with that. I think we did have a very simplistic situation. We may have captured something that's very stereotypical because of the simplicity of the task. And it would be really, really interesting to try and use this kind of regression approach or something similar in something where the perceptual demands are more complicated. So anyway, so thanks for a question. I've got another one from Sammy here that says, were there important differences between participants regarding sustained attention phase duration and decision phase duration? I guess you mean the length of the tasks that I'm showing. Yeah, I think there was. It was maybe a couple of minutes, as I said before. I think the difficulty in answering that question is because everyone spotted the ship at slightly different times. So the watchkeeping was generally between 4 and 5 minutes, and the decision making was generally between 3 and 4 minutes or something like that. So there wasn't an awful lot in it. We tried our best to try and keep the phase as consistent as we possibly could, given that we're dealing with those individual differences. And I have another question from Gerard, who said, have you looked specifically at the NIRS data of people who reacted extremely slowly? No, we haven't. That's a really good idea. Because we could see them, it'd be interesting to see if they're outliers with the fNIRS data as well as outliers with performance. But we haven't tried to do that. And maybe, I know we had 40 people, but they were kind of quite different to one another. So I think if we'd have had more people, I'd have been more inclined to go down an individual sort of route. But having said that, Gerard, if you think about it, when we did the regression across the individuals.
Maybe there is a problem in the Stephen connection. Steve? Okay. He's back. Are you back? Only you are muted.
I'm sorry about that, everybody. I have no idea what happened. I'll try and get back to the chat. I don't know. I think I just cut out before. I was answering Gerard's question. And Suzanne's just asked me another question, so I'll try and take that. So how long does it take to identify an obstacle to the actual avoidance in this particular scenario? I'd say roughly around 10 minutes. approximately around 10 minutes, depending on when you spotted it. So that's what I think happened there. Okay.
Okay. So, any other questions?
Yeah, it was quite long. Suzanne, I'll answer the question in the chat now. Sorry, Susanna. Yeah, it was quite long, but Suzanne, things happen over long periods of time in at sea. It is quite different to what we are used to on the roads and other places.
So maybe thank you, Steve, once more for your kind availability in sharing with us your knowledge. And before the greetings, we would like to inform you that there will be another Human Factors and Ergonomics Society Euro Chapter remote keynote given by Professor Wendy Rogers on the theme Recent Advances in Design of Robots to Support Successful Aging. It will be on December the 2nd at 4 p.m. Central European Time. So we hope to welcome you again at Professor Roger Talk. For now, thanks for joining Professor Fairclough keynote that Steve allowed us to post on the Human Factor Ergonomics Society Euro Chapter website, so you and your colleague could listen to also in the future. Thank you, Steve, once more. And stay safe and healthy.
One thing before I go, Antonella.
Sure.
Someone has asked, when will registration for the next meeting open?
I don't know. I suppose Dick Dewar will send the announcement and on the website of the Human Factor Ergonomics Society website. So you can stay tuned on our website in order to receive the information.
I think it'd probably be maybe Christmas or early in the new year.
The Wendy Roger talk will be on the 2nd of December.
No, I'm talking about the registration for the next meeting.
I don't know.
For the next meeting in Liverpool next year.
Yes. The registration. We will end the abstract receiving by, if I will remember, beginning of December, and maybe in January we will have the registration open. I suppose more or less it's this timing. Sorry, I didn't understand.
Yeah, no problem. Yeah, okay. Yeah, anyway, thank you, Stefan. Stefan's putting stuff in the chat of the link.
Perfect. 5th of December. Okay.
Yeah.
By the 5th of December, we will receive abstracts, and then I suppose in the beginning of January we will start with registration.
Okay.
Thank you very much. Stay safe and healthy. And see you again remotely in December and live, fingers crossed, in April 22 at our next conference in Liverpool, kindly chaired by Professor Fairclough again. Thank you, Steve. Thank you all.
Thank you. Bye-bye.
Take care. Bye.